Distinguished participants, welcome. Welcome back. I wish you a happy day, a beautiful day. You attended all the meetings until today, and you are well acknowledged, pretty much acknowledged about what's going on, what the technology is about, what's going on in the sector, whatever. And in this section, we'll be speaking about new technologies in renewable energy and our manufacturers' experiences in out markets. As you know, wind energy sector, especially the manufacturing, on the manufacturing side, technology advances so fast. I mean, almost every 6 months, new models emerge and new turbine models are marketed. It was said yesterday 2 megawatt platforms are being replaced today by 4 megawatt platforms. Tower heights, blade diameters are all on the rise. More network compliant turbines are being marketed today. A very fast technological development is on the go. It is said that about 8,000 components are in a turbine, and each one of those components are prone and subject actually to a very fast paced technological advancement. And when it all comes together, you have at the end of this equation, you get faster, more efficient, more capacity. So that's where it is all going. And we talked about also capex, opex, reducing. We talked about these issues, the entire environment, sectoral environment becoming more and more competitive. We talked about all these issues. Now we are 7 on the panel, and we have a time of 90 minutes, an hour and a half. So each one of us will be granted 15 minutes. So, without further ado, without stealing further from your time, I'd like to start with Mustafa. Mustafa comes from Vestas. He's a senior sales manager representing Vestas company. So, let us ask you, what do you think about our topic? Hello, everyone. The history of our sector goes back as 4 decades. It was 1970s. I think the first commercial operation of a wind turbine was realized. And as Mustafa says, in the last 5 years, especially in the last 5 years, the sector has seen such a development. The pace of new products being marketed, I mean, it's a leap. It's not a pace. It's a leap, a very fast leap forward based on two pillars. One of them, competitiveness. The years with subsidies is well behind now, and the wind technology, this wind sector can stand on its own feet. It's an independent, autonomous sector and a renewable energy source, of course, based on a renewable energy source. So it enables us to look into the future with confidence. And how should our actions be shaped into the future? How will we mature our strategies into the future? From a commercial perspective, there's this competition between turbine companies, and wind is an alternative. I mean, sun is the alternative to wind. Let's take it so, which brings down costs further. It's a prerequisite that we curb down these costs. And about the future, without coming up with any prescriptions, I'd like to remind you where we have come from. 1984, this is the first wind turbine. 1984 in Turkey. I mean, look at the size, look at the nominal rate. It's about, and this is what it has become. This is what it has become in about 40 years, 30 years. Blades longer, taller than 100 meters, and 3 megawatts, 4 megawatts of nominal power. So 30 years and this change. Has it been a long time? Could it have been shorter? Well, the answer to these questions, I think it's evident. Because you wouldn't know how fast you can run before you can fall. You got to fall. And this is a costly process. This has been a costly process for us. Before I continue, let's take a look at technical problems we encounter in designing turbines. Unfortunately, turbine companies, wherever you go in the world, which climate, they have a limited amount of design specifications to be able to serve in every climb. And today, where we are at, we are face to face inevitably with the economy of scale, and that's how we come up with our products. So you have turbines you use in the polar zones, and you can make small modifications on it and put it in a desert. That's what you have to do. This might look like extra costs, but there are shared platforms, so energy costs. If you're looking for the lowest energy cost, then this is the requirement you have to stick to. Then offshore, you see offshore posts, you see desert or polar environments on the screen. So these are machines that are designed to work in all these theaters. I would like to skip these slides, but I ask you where we have come from. We have come through a lot of curves, a lot of swerves on the road. I mean, blade diameters, whatever, those were the psychological side of the problems. Then we had problems with components and materials and lessons learned from that. But of course, as a result, we can see that we are not working with the same number of turbine suppliers we've been working with 15 years ago. Only a handful of those people remained, survived, those who did a good job and those who were appreciated around the market. Um, the turbines sector, and since its inception, since it is becoming mature, we've been drawing lessons. We've been drawing lessons and using those lessons in new products so as to leave the least room, I mean, hopefully, no room for mistakes. We have no room for mistakes today and no tolerance for surprises. Today, that's the situation because we are looking to minimize nebulosities. I said shared platform. So our prescription for the future is this shared platform, proven performance, field performance, reliable performance. You may not know about the wind, the force of the wind, but you may well know, very well know, how your machines will react. So that's important for us. Two main product gams or families. We have 13 types under two families of machines, and six of them are brand new versions. Thanks to our experiences, past experiences, we made best use of them. We monitored, and that's how we designed these new products, and that's how we work, learning from our experiences and using our experiences in our new products. And very briefly, there's one thing else that I'd like to touch upon. I think one of the meaningful or sane and sound turbines for our country, especially in the central Anatolian region. I'm not saying it's class 4, but in line with IECS standards, this is a good machine, a new type of machine, new design. We 120-2 megawatts. This is what we have in mind. This is what we will offer to the Turkish market. I think it's going to be accepted because today the remaining projects, and look at them in the Turkish market, of course, and look at their wind profiles, and consider the profiles of turbines that can be used in the open. Class 1 or Class 2 machines are robust, but extra robust. And because of this robustness, they will lead to decreased annual generation. That's what our feasibilities tell us. And this robustness, I mean, if you opt for this machine that I'm signaling, it's going to be more feasible. We talk about 20 years, 25 years. So I think 20 years, 25 years in the future will necessitate that you use such machines. I would also like to talk about smaller scale machines. We're sticking with 3 megawatts, and now we're coming up with 4 megawatts. It's the generation 4 in the 4 megawatt platform. This is the new machine, you can see it. The testing process was 2 years, and we're on 3 megawatts. So this is the product GAM. Since June 2017, it's around the new products. So the 4 megawatt nominal power machines with different blade diameters, new models, we are offering it to the market, especially for the Turkish market, especially for global auctions. I think it will be used. We 150. V150 is a nice model that we've got, and let me tell you about it. V150, the blade diameter 150 meters, nominal power 4 megawatts. How do we decide this? Why 150? I mean, why is it not 164, 152, 180? Why 150? And why 4 megawatts? Why not 6? Why not 7 megawatts? Why not 2 or 3 megawatts, but 4? You may ask these questions, and there is a design phase, the development phase, which is which we go through slower. But a gradual increase is required in terms of smaller modifications on the blade diameter on other components of the turbine so as not to leave any room for any surprises. That's how we design our turbines. And that's how we offer you these products. As I said a moment ago, um, well, when you compare these machines, this is a comparative grid, a comparative diagram, regardless of the company, manufacturing company, you can have larger blades, larger nominal power, but it's automatically, you cannot say it will automatically generate more. No, this is a comparative study you see on the screen, and this is where it's gotten to commercially. Uh, you can see the alternatives, base load plants, and similar or even lower energy costs are on the screen. I mean, this is the economy of scale, isn't it? And these are the sizes. And but about dimensioning the turbines, about those criteria that we use to dimension our turbines, the only thing is the least of all costs. So, hence our decision for 4 megawatts and 150 blades. We believe, and we claim and challenge everyone that this will be the least costly product in the future. And this was the traditional part, and I think from this slide on, it will be more exciting and more interesting. Again, on the basis of our experiences, we're developing new models. Yes, that's an ongoing effort, but still we're looking for things new, which are new because we must do it. I mean, it's a must. Turbines have always been with three blades to generate electricity which could be connected to the grid. They always had three blades and vertical type. Always. That's been so. But you see on the screen, this picture, this is operated and this is functional actually in Denmark, and it is going through its testing period. This is an onshore. And I don't think we'll be seeing this in the onshore environment, but it's going to be more meaningful and applicable in the offshore environment. Still, this is the test, and the test is ongoing. In an onshore environment, we have to see the aerodynamics of this, the aerodynamic performance. We want to know this, know the details of its aerodynamic peculiarities, and this is a part of a joint research project with the Danish University. Well, when you look at it, facing the machine, and take a look at the materials used and the costs, you can see that it pro rata with its cube. Well, this is the question we had. Instead of one machine, you can have four smaller units with different sweep areas, sweep zones. Onshore it's not meaningful, but I think it would do. It would serve the purpose in the offshore environment. Yes, in the offshore environment, maintenance is a problem. It's costly, and when it is so, performance of one turbine when divided into four pieces, that would increase availability. That's why I'm saying it's going to be better in the offshore environment. But in order for this to, it's not even a product yet, so it's too early. These are assembly pictures. Apart from research, we are also doing modifications on new products so as to minimize the cost and maximize generation and efficiency. In areas such as Central Europe where we don't have harsh winds and where the developers feel the need, urge even, to go high, Well, use of steel and concrete is one option. That's what they're working on, or larger blades, thinner, um, thinner towers, and this is one example. Line tension to reduce load, which would in turn reduce cost. So these are the things that we're busy with now. You can see the wires. Basically, for our sector, I think such R&D activities are a requirement. You can follow us on the web and follow what's going on in the last 5 years on the web on the energy storage side, be it chemical, be it physical. There is a buzzing work ongoing on this side, on storage side, coupled with hydropower plants. For example, you have pilot plants and you have multi-coupled batteries coupled with again wind turbines. So Vestas, since 2009, carries out its R&D activities in this regard, and on an industrial scale, we see this project to be more meaningful. This project is the one. You can see the numbers on the screen. Construction ongoing in Australia, about 45, 60 megawatts. I think 15 solar, 45 megawatts from wind. This is the power plant that's designed in Australia as phase one of a bigger project. And they're working with a group of batteries, series of batteries. So this is an experience we're chasing after. In 2018, there will be other plants. I would love to share with you other experiences, more detailed experiences from the operation side as well. But this is what we have at the end of 2 years. And actually, we have not experienced anything new than what we all have been experiencing in our sector. But I think this is where the future lies. Speaking of wind, speaking of renewable energy and other stakeholders, hydro, solar, other components of renewable energy, of course. I'm not talking about reservoirs, but I'm talking about non-storage or low-storage channel type hydropower plants, of course. These are the alternatives to sun. These are the alternatives to wind. And investors have some requirements. For example, the imbalances in the day before markets, the guaranteed amount of generation. These are all problems, and in order to be able to catch up with those guarantees of generation, you have to take into consideration certain things, and there are certain times when prices are high, and you want to supply the market when those prices are high, and these are inevitable strategies. But apart from them, from an operational or network operations perspective, such a joint plant could offer more network stability independently from wind, from solar, whatever, because it's a joint practice, and I think it will be accepted, embraced even, and faster. I hope next year I'll be able to see you again, and I'll be able to share with you further experiences. Thank you.
Evet, biz de teşekkür ediyoruz.
Thank you so much. Now, I'd like to invite Bilgehan Yaşacan, sales manager from Siemens. Yes, please.
Bu sunuda ilk önce yeni çıkacak türbinlerimizi direct.
First of all, I will try to give some information about the turbines that we're planning to introduce to the market. We have merged with Gamesa company, so I'd like to give you some information about Gamesa. Siemens, Wind Power, and Gamesa merged in April 2007, and the press information press declaration was provided in 2016, and Gamesa was established in 1995 and has a very large wind power capacity in various countries, and it is also engaged in many other fields. And Siemens Wind Power is also a company that entered the market by acquiring the Danish Bonus Energy in 2004, and they built the first offshore wind power plant in the world. And these two companies merged, and they have an order book of 20 billion euros, and they are active in more than 90 countries, having 27,000 employees with an annual revenue of 10 billion euros. And currently, the installed capacity worldwide is 75 gigawatts, and the market capitalization is around 14 billion euros. Siemens Wind Power has a history of onshore and also for offshore. We have experience with the Gamesa, and we are the largest wind turbine producer in the world. And when we look at the old Gamesa, you see that there are locations and factories in different parts of the world. And once they merged, we now have factories in Morocco, China, and other countries. We're now about to access to the whole world, having production locations throughout the world. And after the merger in April last year, and after this transformation, we have more detailed knowledge, and we have the big data, and we know that the experience, the knowledge of Siemens and Gamesa were harmonized, and now we are in the process of optimizing all this information. All the wind power, wind turbine investors aim to have the maximum benefit from the power plant they install. And we know that 80% of a power plant is composed of the turbine, and therefore we're trying to ensure that maximum energy is produced with the lowest cost possible. We're trying to reduce the costs, and as Siemens Gamesa, we are trying to focus on all the concerns of the investors. And we have two types of turbine technology. We have direct drive, and also we have the gearbox turbines. I would like to start with the direct drive. This is a new product, and it will be launched in 2019. And this is the profile image of direct drive turbine. And when you have direct drive, first of all, you put away the gearbox, and therefore all the assisting equipments are going away, and the mechanical parts is reduced almost by 50%. And this is how it looks. You only have the electrical panels, and this is a simpler technology, if you put it in other words. And I believe that next generation turbines will be produced in three classes. The motor diameter will be 120 meter in class 1, and 130 meters for class 2, and we will have better capacity, and we will also have 142 meters of rotor diameter for the class 3 turbines. In direct drive turbines, we mostly focus on the areas where there is a po- position limitation, and we will put them at the minimum position so that we can have the maximum capacity. And for turbines lower than 3 megawatts, we will try to increase the surface area and have the maximum efficiency accordingly. And for the gearbox turbines, geared platforms, the portfolio of Siemens Gamesa is mostly for those that are lower than 3 megawatts, and now we will go try to go up to 4 or 4.5 or 6 megawatts. We have this turbine that will serve for three classes, and 143 meter of rotor diameter will be used in class 3, and the nominal power will be 3.5 to 3.9 megawatts. And for the 130 diameter, the nominal power will be 3.9 or 4.2 megawatts. And for 120, we will have 3.9 or 4.3 megawatts. These are the new direct drive turbines, and here you see the technical information about them. The aim here is to have the same nacelle platform for all three types, and the class modifications are easily done, and this is the concept we're focusing on. And if the platform is changed very frequently, it's not something preferred. There are many reasons behind it, and one is efficiency and productivity, and also it requires more R&D activities, and it also reduces costs if you don't change it, because it takes 6 or 7 years to build a platform, and it's around 200 million euros until you introduce it into the market. So, as the turbine producers, we are making some large investments. Here you see power curve comparisons of all these three turbines, and we have this in the market, and the generator softwares and also other modifications will be made on the software, and it will be available. And you see the difference, it is 14% energy increase, and this one was launched and promoted at a fair, and the prototypes will be certified, and the tip certificate will be provided at the end of 2018, and in the first quarter of 2019 it will be launched to the market. And when we look at class 2 130 rotor diameter, and the production is at 3.6 megawatts, and it will go up to 3.9 and 4.2 megawatts, and you see the increase, that is 9%, and it will be built on the current platform. And similarly, this one was also introduced and promoted at another fair, and the certification will be completed in the first quarter of 2018, and in the first quarter of 2019 the production will start. And this is the class 1 type turbine, and this one is the one that will be operating in the harshest conditions, and we see that it is 3.4 to 108, and it will be upgraded, and it will go up to 4.3 megawatts, and it will have a rotor diameter that is 120 meters, and I believe that there are no other turbines similar to this one, and it will also be produced in the first quarter of 2019. And when we look at the geared Siemens Gamesa turbine, this is the second one, and this one was also launched, and 2.1 megawatts, and the rotor diameter is 122 meters. This is mostly for the India and China markets, and then we will decide which markets to go from then on. This is recently launched, and we know that the prototypes will be completed by the end of this year, and the type certification will be completed in the second quarter of 2018, and the serial production will start in the third quarter of 2018. When you see the difference between the rotor diameters, blade diameters, and power density is very good because the generator capacity is low, and its area is relatively larger, and for the class 3 areas this could be used especially in the areas where there is less turbulence. This type of turbine can be sold more. The wind turbine producers, not only Siemens Gamesa, but also others, are doing their best to have the best benefit so that we can increase the energy level. We are working on this, and we are uh, trying to improve the power curves by some softwares. For instance, in areas where there is a very fast wind, as you can see here, we have the adaptive control system, and according to the system, you do not directly go up to the nominal power, because if there is a very harsh or fast wind, in order to protect the life cycle of the turbine, and for other reasons, we are trying to have smoother shifts. This way, there is less wearing on the turbine, and we know that when the turbine works on nominal power, it will not stop itself or lock itself, but there will be a smooth shift, and this way the adaptation is ensured. And this is the high wind ride through, and when there is an extreme wind, turbine tries to go down a little bit, and rather than turning off the power curve immediately, bringing it immediately down, it just goes gradually. And this is not only available in Siemens Gamesa, you also have this feature in all other turbines. You can find them in other turbines as well. And this is the high temperature right through, and if the temperature goes up, there is an adjustment to it, and with a suit ramp down, we try to put it the best way possible so that we can have more efficiency in energy. Let me talk about the offshore a little bit. What's new with the offshore? As you know, in the offshore power plant, in order for you to have an installation, there is a depth for 30 or 50 meters needed, and you see that there are some small power plants built, and we have the floating wind turbines, and those are just knotted to the sea base, and they are not on ground but within the sea, on the sea base. They are fixed, and this way, especially when there is a higher wind capacity, they can be used. And it's planned to have more and more of those floating wind turbines. And here you see how it is transported. And with these turbines, we will be able to reach higher figures in offshore. And I believe that the offshore power plants and their capacity is around 10 to 15 gigawatts, and it's much lower when compared to onshore. But we also have very important developments, sorry, megawatts, and the blades will be larger, and of course you have the chance to be mobile on the sea, but on onshore it's not possible to move from one place to another. I mean, it's hard, and this is why it cannot be used. This is the end of my presentation. Thank you very much for your attention. Thank you. I read an article a couple of weeks ago, and it was said that the turbines will start to float, and it's the same thing for the solar. Now, the third speaker is Özgür Uzun, GE Renewable Energy Region Sales Director.
Sayın Moderatör,
Distinguished moderator, representatives of turbine manufacturers, distinguished guests, dear participants, my name is Özgür Uzun. I work at GE Renewable Energy, and my branch is onshore. So I'm representing the onshore side of our business. For long, I've been watching one thing which was very important, the topic, let me say, and this is the first time that I'm attending. This is the first time I've been given a chance to offer you my views from GE perspective. This is the first time I have this opportunity to tell you about new technologies on board with GE, but things are hectic and very exciting in today's world, especially speaking about wind technology. So what does this mean exactly? Take a look at the last couple of years. The support mechanisms that we enjoyed were there, but wind energy is now becoming more and more independent from these subsidies and incentives and support mechanisms, and we see it, each and every one of us. And in this context, electricity generated from wind energy and its costs we want to reduce. And we talk about new technologies. What can be new technologies in wind turbines? Output power can be increased, larger rotor diameters, more efficient units, longer blades. Of course, they have their limitations. So we see that it's not easy. It's not easy, but it's not also without a solution. But because we have information, we have the experience and knowledge to support. That's how we come up with new technologies as such. Within this context, it was 2 months ago that we launched 4.8 megawatt 158 next generation onshore wind turbine. I would like to tell you about this new GE onshore wind turbine, but very briefly and to the point. See this unit, 4.8 megawatts, that's the output power. 158 meters of rotor diameter, and about 170. That's the blade length. This is, I think, specifically designed for Turkey, don't you think? And the reason is that we think this is the turbine of a scale which would minimize electricity costs. This unit, from the Turkish perspective, is a good one. 100 and for Turkey, there are two options: steel towers, 120, 121 meters. Yes, it will be used on a steel tower. How about the wind class? It's good for IEC as for mid and low level of wind GE has other models, as you know, depending on certain limitations, depending on wind classes or categories. So that's why we have numerous platforms. And the platform 3.8, which houses 4 megawatt platform, 4.8 units are the first family members of this GAM of products. And you can see it on the screen in areas where you don't have enough room. And Turkey is an example to those countries which don't have enough room. That's why we're looking forward to taking up lesser space but coming up with higher megawatts. So, from this perspective, at low winds in congested areas, we see this new unit 3.6 136 on the left. That's the one. It's presently being used in Europe in the global market as well as in Turkey. Yes, 3.6137. That's one of the solutions we offer to our clients. Again, in Turkey, we use another 3.8130. Yeah, 130 signifies the rotor diameter for mid and high speeds. Let's take a look at 4.8. Get back to it. Yeah, 4.8 is a different design. And one of the important components of this design, one of the most important, is that the nacelle is larger, fairly larger. The nacelle, or the machine room, so to speak, is big, and this is justified by ease of serviceability. The technicians, engineers, when they service and maintain, will have room, better room, larger room, and also control systems and all electrical systems are on the nacelle side. Thanks to this, electricity losses are minimized, which further enables the more effective use of this unit. 4.8, when you compare that with 3.6 137, yields or produces 30% more. The capacity factor, I mean, if you look at this from that perspective, 146, 149 are the capacity factors, so this makes this unit a very efficient one. 7 to 8 meter per second band, that's the bandwidth I'm talking about. In low winds, 138, 140, that's the capacity factor. In today's world, especially in competitions and auctions, we value one thing, and I think you value this very same thing, this unit in your projects. Yes, this is a good piece designed for the upcoming 2 years, and site deliveries will start in the upcoming 2 years. That's 4.8158 for you. This is actually my presentation. This is what my presentation is about, concise, to the point. But as a panelist, as a member of the panel, I'll be most happy to be able to respond to your questions. And if you want to discuss this unit in further details, I'll be available. That's also the same reason why I try to keep it as short as possible. Thank you. Thank you. And next, John is oh, I'm sorry, Typhoon, and we're missing someone? Okay, Enarkon Typhoon, please. Well, I mean, now it's, I see it's Yunus, but Typhoon. No, okay, there's a confusion with the names. I'm sorry for I forgot the microphone, so let me rewind. Thank you for your time, most valuable time. Yunus Yeah, we were planning that Yunus would come and do the presentation and represent our company, but he's sick, so I have to take over and sub him. And in line with the topic, I'll be talking about novel technologies, what we have in Enercon, especially the new 4MV turbines. But before that, let me tell you very briefly about our company, some general information and facts and figures. And also, I will touch upon the differences between our new and old technologies. Enercon, as you know, was established in 1984 in Germany. Today, in the world, 47, 46 gigawatts, that's the threshold of our installed capacity. And in the world, we are carrying out sales activities in more than 30 locations, 30 locations. You can see them on the map. And this is the region where Turkey's at, zoomed in, and manufacturing facilities are there, own investments. That's how Narcom works actively in these areas, in those factories. In Turkey, however, we established our business in 1997. That's the date of entry into the Turkish market, and now our office is in Ataşehir, Istanbul. That's our sales office. Also, we have another office in Izmir. Enercon Finance and Project departments are in Izmir, as well as Service and Maintenance departments. Those are the ones in Izmir. In 2002, Enercon's first investment in Turkey was the Aeroblade factory. It was established in the Izmir Free Zone, and I think E82, 92, and 70, those blades are manufactured here. Approximately 31% of rotor blades are produced for the local market, and 69% of rotor blades are manufactured for the international markets. Also, in Izmir, Torbalı, we have a concrete tower factory. Apart from that, we have suppliers all over Turkey, especially regarding the supply of steel towers. Enercon turbine technology is based on direct drive. It's actually one of the forerunners of direct drive turbines. You can see on the top section, see the generator, rectifier controls, excitation, pitch drives, and yaw drives. And under the tower, you have the transformer and power panels. The working principle is as such. If you could run, dear friends, if you could run the video on the left, bottom left, I think our bottom left video. Uh, so that you'll be able to see, yeah, multipolar rotor connected directly to the wings, the blades, and coiled stator. The kinetic power coming from the blades relate to the rotor, and at the stator, it's a smooth system, like bicycle dynamos. It's the same. I mean, almost the same mechanism with bicycles. Could you please run the second video as well? This is the factory in Germany. You can see the stator coils. It's handmade, 100% handmade. So the when I mean this is the magnetic current. Kinetic power comes from the wings, and stator converts that to alternative power. There are two pieces manufactured here. The stator, you can see the stator. Again, rotor poles, entirely modular. It can be replaced and maintained so easily. Yeah, of course, replacement is so easy. So this is one of our existing products that are existing in the market for the last couple of years. In the upcoming years, there will be major changes for our company, for Enercon. Working philosophy will remain, but instead of copper, we'll be using aluminum coils. You can see here gearbox type or direct drive type systems. We don't have any hydraulic bearings, whatever, in our systems. And from a platform point of view, in 1995 until today, Enerco has experienced a lot of growth. And with the new series that are in the pipeline, E series, E14, 1120, 6138, those are the ones where we will be using the aluminum coils. Enercon, again, manufactures class 1, 2, 3 turbines. The red ones are the new ones, new arrivals, and the empty one will be filled in, empty box will be filled in with a new class 3 turbine, and very soon so. In terms of design, yeah, the EP3 series, you can see a slight change. It's an egg-shaped. It's no longer egg-shaped at the nacelle, and the generators, no copper but aluminum foils and coils. I'm sorry, and there will be a flatbed profile, which is the new design for blades. Let's zoom in to the left. This is the copper stator, copper coil stator, and the new aluminum design on the right. You can see future technology, four-moved aluminum coils in the stator. And the objective is, of course, to ensure a magnetic field which we used, uh, for which we used coil. And we'll be using aluminum, it will be lighter, the loads on the turbine will be less. Again, EP3 series turbines, easy to assemble, easy to install, so it all translates into cost reduction. That's why we have them in such modular forms. As you can see, the generator rotor is tripartite. It will be produced in 3 parts. In terms of design, you can see the change here. At the bottom picture, you see the egg shape. And the gray portion is the EP3. It's 127 megawatts, different tower heights. So you have different models. Next year, prototype assemblies will be carried out in 2019 in the quarters 2 and 3. Certification efforts will bear their fruits, we hope. We call it EP3 series, although the turbine power is 4 megawatts. 3 megawatts, 3 megawatt platforms was the basis. Electrical substructure, again, is based on the previous models. That's why. Again, in the blade, you can see the spoiler is no longer there. As I said, it will be a flat back design to ensure as static as possible a blade, free from loads, excess loads. E138 Class 3A, that's how it's going to be marketed. Again, aluminum coils, 81, 111, 131, and 160 towers are envisaged for this platform. Again, one thing which is important is that the series will have its design lifetime, which will be, from an economic perspective, 25 years. The standard in the sector, or the sector average, is 20 years, but our design is for 25 years to enable long-term calculations to be carried out by investors. You can run the video once again. It's an introductory video about the turbines.
Tekrar basabilir misiniz? Arkadaşlar klasörün içerisindeki videoyu direkt oynatabilirsiniz. Evet. Kulenin alt tarafında yine trafomuz ve güç ünitelerimiz bulunuyor. Özellikle enerjinin üretildiği kısımla yüksek gerilimi birbirinden tamamen ayırıyoruz. Alüminyum sargı kullanılması
Aluminum coils make it lighter, but we have a similar magnetic field, but it requires you to use more coils. But the generator in 126 series has a diameter of 30 meters. It has to be thicker to come up with a similar magnetic field. You can see the aluminum coils, the stator, and multipolar rotor.
türbünün naseli
This is the nacelle portion of the machine house. It's simplistic, not congested, to enable free maintenance.
kanatlarda yine trailing acceleration dediğimiz gürültüyü özellikle azaltmak amacıyla
This triangulation on the blades is to reduce noise, hence these notches, but blades will be manufactured in single pieces.
Normalde videoda 3,5 megawatt olarak
In the video, the power curve is 3.5 megawatts, but with an update, it's 4 megawatts. It's still 3.5 in the presentation, but it's updated to 4 megawatts. So, well, the main objective here is to act in tandem with plummeting costs, power costs, so we are trying to adapt ourselves to this new market condition. Hence, we are taking action in this direction. We are carrying out our work in this direction for many years, and finally now, aluminum coil forms, more compact, easy to assemble on site. These are the ones, the specifications, the features that we've been looking for and we've ensured. So this is the new series that's in the band of production, and we'll be installing it in 2019. And finally, Enercon services. I'd like to tell you about our services. Generally, in Turkey, this is a service format we offer. It's called EPC, Enercon Partner Concept. We have 776 Enercon wind turbines erected in Turkey, and in all of them we have EPC for 15 years. So that's full maintenance and service. For 15 years, we are providing support to all technical glitches for a duration of 15 years, and it's all under an Enercon guarantee. What's going to happen in 15 years? We talk about design lives of 25 years, and after 15 years of full service, what's going to happen? What can be offered? That's one of the topics we are working on, because people ask us about this. And also, again, we have alternative service packs. Especially after 15 years, we have EPC2, which is only transport and crane deducted. And another alternative, you take out repair and replacement of major components. That is EPC3. So major component replacements is taken out in addition to special transportation and cranes, and the remaining green portions are EPC3 components of the EPC3 service maintenance schedule. And finally, you can see we have about 352 service stations worldwide. Turkey is no exception. We provide these services through Enercon services, and I'll be here and most happy to respond to any queries. Thank you for listening.
Evet, Tayfun Bey, biz de teşekkür ediyoruz.
Thank you very much, Typhon. The next speaker is Can Yılmaz from Nordex. He is the wind farm and project engineering manager for Turkey and Middle East. Distinguished chair, distinguished speakers, and distinguished participants, hello. I will be talking about Delta 4000 turbines we have, but before that, let me give you some information about our revolutionary development. In 1985, Nordex was established in Denmark, and in 1978, we've produced the first turbine. In 1995, we produced the first megawatt turbine in the market, and in 2000, our activities were brought to Germany, and Alpha was the first turbine we produced, and we also have the Beta turbine that was in the Turkish market in 2007. And then, based on the changing requirements and market, we started to produce Gamma series, and then we went to the Delta generation, and we still go on with Delta. Tomorrow we will have Delta 4000 series. This is going to be the turbine series that I will introduce you today, and all these turbines are designed and produced based on the requirements of its time. And of course, we have technological changes, but also conceptual changes in our turbines. And after the merger of Nordex and Acciona, the cost of energy is the aim, and our aim is to reduce the cost of energy, and we are trying to have the lowest unit energy price. And also another aim was to simplify the turbine by ensuring that the high quality is preserved. And when we look at this, the design lifetime extension is up to 25 years, and we see that we have a larger sweeping area by 39%, 30%, and the rating is 25% higher, and it is ICS class type of turbine. Well, of course, when I say tomorrow, we need to have a look at the schedule. In 2007, we started the publication process, and publicization process, and then we will start the tests in 2018, and the series production will start in 2019, and we are aiming to have the first installations in Turkey in 2019. When we look at the turbines and when we compare N131 to N149, you see that there is a production increase by 28%, which makes Delta 4000 the best machinery in its range. And we will have three versions: 4000, 4380, and 4500. We know that for different sites we will give the the best option. When we look at the tower portfolio, we will have 105 meters and 125 meters. These are two towers we will have. And in the European market, we will also use hybrid towers that will go up to 64 meters. and the lower section is concrete and the upper section is steel, and the steel towers will continue to be as modular steel towers. When we look at the changes compared to delta turbines, there is an increased rotor diameter and forced pitch bearing to handle loads, and we have this system, and also transformer and converter are in nacelle. As I have told you, the turbine is much simplified, and despite all of them, we have the same nacelle diameters, nacelle size. And when we look at the nacelle, you see the right part, the yellow part is the is the switch cabinet, and just opposite to it we have the transformer, and behind it there is the converter, and we have the more better options here, and you see that the blade design is a bit different, and it's a single piece, and it is larger, 9 meters larger than NR65, and we have the serration systems for anti-icing and noise reducing. We have the glass fiber and also a composite material, and we also have the lightning receptors at the same place, and here you see the scheme of two different blades. Another difference with the blade design is that we have the bolt connections, T-bolt connections, but now we will go for SSP root joints. And when we look at the difference between the two, SSP tools are lighter and there is more weight capacity, as you can see in the graph, and we know that the longer blade will be heavier, therefore we're trying to deal with it that way, and we have the SSP tools and parts ready-made in the factory, so we do not have an extra effort for producing them like we do in the T roots, T bolts. And when we look at the yaw system, we had two yaw engines on the right and the left in the past, but we will have four of them, and sorry, six of them, and we also have some changes in the braking system, and the current caliper system will be replaced by electromagnetic braking, and the yaw engine will also act as a part of the braking system, and we see that it will be working in a larger space. And when we look at the differences, it is more silent and it's faster. And this is inside the turbine, and we have the transformer, and these are in the nacelle, and therefore the cables are replaced by a single cable that will act, or that will work for the others. And of course we have energy saving here, and 1% increase in energy production, and we see that it will take shorter time to build the nacelle and the tower. Transformers require some sensitive engineering touches, and here we will use the dry transformers until 24 kilowatts, and when we reach 36 kilowatts we will use synthetic ester transformers, and we know that this type is an area for enclosed areas, especially, and this has been used since 1970s, and this is the one of the best products you can use in enclosed areas, and it has a very high level of availability. Sorry, biodegradability. And when we look at the cooling system, we have the delta cooling system, and we have the heat pump on the nacelle, and we use the atmosphere as a heat uh, area, and we will transfer it inside. And let me talk about the reactive power of our turbine. With the current 3000 series, we reduced the cost in this key value way down. And when we look at the Delta 4000, we bring it down to 0.84 or 0.85, so we will not have any problems about the reactive power at the connection phase. And let me talk about STATCOM function. And this one was also available in Data 3000 series. And reactive power support is always considered when there is production, but we know that the capacity of energy created by the reactive power cables can be problematic when there is no wind. Therefore, with the STATCOM function, we are trying to allow reactive power provision irrespective of the active power provision. In this way, we're trying to avoid from the penalties that could come up. This is the end of my presentation. Thank you very much for your attention. Thank you. In this session before lunch, there was a female speaker, and we will have a female speaker as well. Yes, please, Sammy. Hello, distinguished chairs, distinguished colleagues, and participants. I'm from Sanvion, and I'm working at the New Markets Department in Hamburg. And I'm also working on commercial and contract management. As you know, Sanvion was founded in 2001 by a merger of various companies, and it was called Repower at the time. And all these companies are engaged in engineering, and this is why they were so open for innovation. And Repower mostly focused on offshore, but we also had onshore turbines as well. And the name of the company changed, and it became Senvion at the time. And now we're still working around the world. You know that it's a German company, and most of the um, turbines are installed in Germany and also in Europe, and mostly the company was active in Europe, but in the recent years, especially 3 or 4 years, we are reaching out to the whole world. We have 7,000 turbines around the world, and we have 15 gigawatts of installed capacity. Of course, we have new team members with different backgrounds and different experiences, and Samvian continues to improve itself, and we also continue to make some innovations and carry out some new projects. And here you see we have a Turkish member in our management level, so this is very good for us, and we are proud of this figure. And we will focus on the new markets and Serbian's market adaptability. First of all, I would like to focus on the three key trends that shape the wind market. First of all, we see that there are different markets in the world, but there are two poles in those markets. One think that there are lots of installations and you do not have a very large growth trend, but on the other hand, you have still installations, but they have larger growth potential. And we know that those two different types of markets help us reshape our market, and also as a result of those two elements, we will have the LCOE, stabilized cost of energy, that that falls fast in a fast manner. Let me start with the first one. We have some established markets such as the European market, and these markets have lots of wind power plants, and their growth trend is much lower. And what are the elements that can trigger those markets? As you know, by 2030, the energy requirement in the world will be 30% higher compared today. And as you know that in those countries, they are trying to transform from carbonization to decarbonization, and for this reason, they are looking for renewable energy resources such as wind and solar power. When we look at the statistics and recent reports, it is estimated that the wind power plant installation is around 5% right now, and it will go up to 12%. And when we look at the annual installations, it will be around 25 to 20, almost 30%. So there will be more and more wind power plants built around the world. What is the role of Sanvion in this market? We know that Zambian is present in 7 out of 10 largest markets up to date, especially in the UK. It's the market leader, and we have a significant amount of installed capacity. And also, we have the United States and India, where Serbian makes significant efforts. But we know that those markets are a little bit problematic because their growth trend is lower, as you can see here. But when you look at the new markets, the blue ones, the growth rate is much higher, and every year they need more and more wind power plants, and more are installed. And Senvion, when dealing with the current markets, they are trying to penetrate to the areas where there is less, fewer turbines, and also in new markets, they're also trying to build more and more turbines. Of course, you are supposed to enter into tenders, and we know that this is the situation in markets, and with the tenders, the LCOE and the grid parities go down so much. I mean, there was around 50% reduction in those areas, and the turbine producers must be flexible, and they need to be acting fast in order to take their part from the market. And Senvion in Chile and Italy have won some projects and tenders, and I believe that it is important if you can adapt to the market easily. And when compared to the other energy resources, wind is an optimum energy resource when you look at the investment cost. And in the onshore wind scale, it's almost less than 100 or even $50. And it's very important to reach the grid parity. I mean, the investment cost per megawatt hour should be smaller or equal to the unit price of electricity. It's very important to have the grid parity because if you reach it, there will be more investors and the funding can be found easily. And according to a report from 2016, in Mexico, Central America, Peru, and Chile, the investment costs and also grid parity is around $37. It ranges between 37 to $55. And the reduction of LCOE is not only something that is for investors, but also the turbine uh, companies need to reduce their own costs. And in the last 7 years, turbine price per megawatt reduced by 26%. And when we look at the price of turbines per megawatt hour, it went down by 42%. So both of them are correlated. And Senvion has a strategy to reduce its LCOE. The first one is to increase the energy production of turbines, and the other one is to reduce the costs. As of today, here you see our portfolio. As you know, a couple of years ago, 4 years ago, Senvion uh, had more turbines with some faster speed, but in the last 2 years after the merger, we have 7 more new turbines, and we have a very large budget allocated for R&D activities, and we're also acting very fast to adapt to the developments in the market. We have the 2 megawatt class, 3 megawatt class, and we have the 114 meters rotor diameter, and also we have the 3.6 megawatt turbine with a rotor diameter of 140 meters, and this was used for a project in Australia. And for 2 megawatts, we have high rotor diameters and we have lower output. And you see that in India, there was an agreement made for a project, and also Senvion purchases the factory in a new market if they want to enter into this new market, and we did the same thing for India. LCOE goes down by 4 to 6% each year when compared to the past, and Semyon aims to have an LCOE reduction by 14 to 18% until 2019. Of course, innovation is very important to do this, and the new turbines are important, the power ratings and rotor diameters are important, and on the other hand, cost is very important. On the innovation side, for developing new turbines, the keyword is modularization for us. It's like Legos actually. We have multiple rotor diameters. We can make use of them because we have a very large budget for R&D, and we can design rotors that are specific for your project, and also we can change the output based on your project. It was 3.6, but also it could be 4 megawatts or different megawatts. We can have all these options for our customers. And also, other than that, the tower length, tower height is also very important, and they are designed specific to your projects, and we have different heights of towers. And on the other hand, when we look at the cost side, we know that there are some strategic countries, and it's very important if they are close to our markets, and if you want to have a new market, and if there is also a limitation of localization in the market we want to enter, we're working on it, and it's important to take these into consideration if you're trying to reduce the costs. And similarly, we can make use of the local producers in the location where the project is. And also, rather than producing 2 or 3 types of turbines, our aim is to produce project-specific turbines that will give the best energy production. And of course, you need to make some variations in your turbines, and this way you can produce project-specific turbines. For instance, we have 90 from 94 to 134 meters height for towers, and we have different sizes of blades, and based on the requirements of the project, we can change the blade diameters. Let me give you an example for a project in Australia. This is 3.2 megawatt, 122 meters of rotor diameter, and based on the wind characteristics of the site, it would be much better if we go up to 140 meters of rotor diameter, and bringing it up to 140 brought extra burden and extra weight, and of course we developed some control mechanisms to make it balanced, and we changed the generator also from 3.4 to 3.6, and we had more energy production, and we used the same tower here, and we just changed the generator, and it didn't cause any cost increase, and it preserved the cost almost at the same level. So this is how we designed it in this project. And as of today, these are the products in our portfolio: 3.4, 3.46 megawatts. Have rotor diameter of 140 meters. So we also have more turbines with larger rotor diameter, and we will have turbines with 4 megawatts that will be available in the market soon. And this is my last slide. On the innovation side, we're trying to reduce the cost on one hand, but it's very important to reduce the cost, because you change the rotor diameter and power output and etc. But if it's still expensive, you will not be successful. Therefore, Senvion has a strategy for this, and they establish factories in key locations, and they buy or they acquire some factories from those countries, and we also need to choose the best suppliers in the area, and also we are trying to use our strategy to reduce the installation duration. It means there is less cost, and also we need to use the modularization approach here as well, and we have lots of moves to reduce the service costs, and project consolidation is very important to reduce the cost of the project, and accordingly, our aim is to have less investment cost, and we need to have a good grid parity so that we can have markets where you can invest in more. Thank you very much for your attention.
Bize teşekkür ediyoruz senin adına.
Thank you. Selin. Well, in a nutshell, we have seen their attainments, their achievements, the manufacturers' product portfolios. They told us that the costs are going down fast, and all these things that we listen to, they tell us, they show us. I think initially there will be auctions. In the near future, 500, 600 auctioneers will be there. Candidates will participate in those tenders, and in the upcoming years, maybe on 2019, 2020, technologies have to be taken into consideration in those proposals. I think that's important, becoming more and more important. There is this very steadfast competition. Every company with their own plans and programs, varying their gams of products, modifying their products, and at the end of the day, it's all of us again benefiting from this competitive prices, lower prices. I don't want to steal much of your time. We can move on with questions and answers. If you have any questions, please raise a hand if there are any questions. There's one. Please. Hello, Tech Fan Construction Company Cihan. We talked about the fast pace of technological advancements. There's this fast development. And I'm asking this on behalf of investors. After a certain time in turbines, I'm not, well, I mean, anyone can respond to this question, by the way. But what kind of upgrades are there to increase generation instead of replacement because it's very costly? Instead of replacing an entire turbine, any minor upgrades, for example, elongation of blades, I mean, that will require a new type certificate, but on the manufacturer's side, do you have such activities, such plans? For example, for duration of YECTAM for 10 years, you don't want no one to touch your turbines, tamper with your turbine, but after 10 years, would that be a possibility? Well, as Siemens Gamesa, we have similar works, but investors should not have great expectations. These are modifications on blades. For example, we can fit the blades with small modifications, vortex generators, etc., to ameliorate power curves, but it does not go from 2 to 3 megawatts or when you increase blade lengths. I mean, it's not technically easy. It's very, very hard technically, and it's never been tried as far as I know. But apart from that, turbine manufacturers normally, when they issue a new platform, new model, they have this generator capacity already. It's inside the generator actually. And once the turbine self experiences, these upgrades can be carried out through softwares. But it's not easy because you have this running turbine, 3 megawatts, for example, assembled, the width, the blade length, all the dimensions have been set for this megawatt. When you upgrade the generator on operation, during operation, there will be excessive loads and it can be hard to make those upgrades. I think this is a short answer to your question. Yes, small modifications is possible, but large scale modifications, don't expect them. I mean, as at least for Siemens Gamesa representative, I can tell you that it's not easy. Any other contributions? Yeah. Well, as you said, enlarging the rotor diameter, it's not an option because the turbine design is optimum. So the turbines have to be also fitted with, I mean, not the nacelle, not the hub. You cannot find anything to meet the requirements from those modifications. But if you're talking about the very old turbines, you can do it with vortex application and ensure a 1 or 2% increase in generation. But at, you can modify certain things at the startup phase, and even using joint generators is another option, but this all boils down to power increases of 1 or 2%. But these are all small scale modifications, and it wouldn't be realistic to try for a large scale. Any other questions? A large scale modification. Any other questions? Yes, sir. Thank you. Enver Kaya. I come from the Organized Industry Zone. I'm the technical coordinator of the Austin Organized Industry Zone. I have a question for Siemens and another question for the rest of all of you. Siemens, here's my question for you. You are establishing a wind farm. Is it direct drive or gearbox type? What kind of a turbine will be used? And let me ask the other question also to other panelists. You are saying 26 years, the life cycle of these turbines, and do you have a graphical performance chart per annum for each year for all 26 years for a turbine? Well, let me start with the type of turbines in the ECA tender. Well, it's not clear yet, let me say. It's not decided. There are two options, and two options are on the table, but inside decisions can change very quickly. I mean, they were talking about direct drive on once they were discussing gearbox, so it's not decided yet, but both turbine types and all feasibility supplier negotiations have been carried out and ongoing also, but mostly it's about to be complete. Well, as Siemens, I can respond to the second question. We have two different types of technologies. Gearbox technology, I don't want to talk about it, comment about it much. I don't know it in further detail, but about direct drive, let me tell you, Siemens Gamesa direct drive technology uses natural magnets inside the generator, and this natural magnet's life cycle in Denmark, I was told by this engineer, it's forever. It's forever. I mean, the capacity will never go down. It'll never sink. Anyone else? The second question was for all the panelists. Yeah. Let me tell you about the second question. Essentially, we talk about 20 years, and the design life cycle of the industrial facility is 20 years. Apart from type certified maintenance, you have preventive maintenances, at least for direct drive and gearbox. This reduction in life cycle, it may be ignored. At least it's reasonable. That's what our experience tells us. That's what we see. Turbine designs, turbine life cycles during operations can be more than 20 years. We have a lot of such facilities, such plants, but I cannot give you at this stage an exact number. But maintenance is critical, and maintenance in compliance with type certificates, use of original products and components, etc., those losses will be ignorable. Thank you for the comments. Acar Soy Energy, Halil, that's my name. I have two questions. One of them for Enercon and Nordex reps. If I'm not misunderstanding, you are no longer talking about 25-year guarantees. This is the service standard, or will it require additional costs, additional fees? And in turbines, you have mostly mechanical components, mechanical equipment. How sound would that be? How reasonable would that be? Could you please provide us with your individual comments? And second question is to Vestas and Nordex reps. As far as I know, both companies have gearbox turbines only. And I've seen it in your presentations that, for example, direct drive or other new technologies were not in there in your presentation. So both companies, are you planning to use direct drive technology, or what other different methodologies of turbine technologies are you working on, if there's any? So please tell me about your future plans. Also, John from Nordex, my question for you is about the transformers. and the main power transformer. You said they are located in the nacelle housing. In addition, you have control panels inside the panel as well. Is this sane and sound? I mean, taking into consideration other factors such as fire, or what measures have you employed? Thank you. Let's start with your first question. 25 years of life cycle on site has to be determined and discussed outside on site because of different wind conditions, different topographies. The 25 years is not possible for all terrains. You have to go and see. It can be 25, it can be 24. So, but it will come out there when you go on site. It's a site-specific issue. Some sites are more rugged, some sites are more smooth. And about the gearbox, our experience as Nordex double fed generators and gearbox combo, I think it's a technology that we will stick to for a while now. It still has a quite a long way to go, and the difference between technologies, in both technologies, there are upsides and downsides. But what is important is how you operate and function and use and maintain and service these technologies and about compatibility, where they stand. If take the example of gearbox and double fed UPSs, in all markets, in all countries that we work at, Nordex can give full compliance. And in markets which are expected to grow harder, our previous work gives us confidence that we will succeed there as well because we have invested dearly to this technology. I mean, the technology is relatively old, does not necessarily mean that it's an old technology. So I can tell you we will go on. Could you please remind me? Oh yeah, transformer. Your last question was about transformers. The nacelle, the transformer being housed in nacelle. Just like in other industrial areas, this is the field practice. These are methodologies that's preferred by many, and how to secure that. And of course, we have fire sensors, etc. Fire sensors and water jets, whatever, to extinguish the fires that's inside the nacelles. And the equipment that we use in these transformers are chosen specifically using materials, industrial standard materials with uh, real high combustion degrees, threshold degrees. Until since 1970, for example, we had no records of any accidents. So it's one of the safest products we can lay our hands on. And dry type transformers, they can't self-extinguish. They don't catch fire. They're not combustible, off combustible materials. But of course, the risk is always there, just like in anywhere else. You're walking on the street and you're faced with a lot of risks. And what matters is how you manage those risks and how you mitigate them. What kind of measures you employ. And on these areas and these fields, we're trying to improve ourselves as much as possible to pass that knowledge on to future generations. And Enercon will try now to respond to this question. About 25 years of design the period. Well, it's nothing new. In the EP3, have 100. We have 25 years of certified, but we have E92, 91, 93 turbines with 25 years for design, and in previous years we have presented here 4.2 megawatt, 126, 144 rotor diameter turbines have 30 years of life cycle. So it's not a condition, and Nercon does not have a precondition here. For example, EP3 126 will be marketed as Class 2A, and when you put it on the Class 2A, the design life cycle is 25 years, and it's independent auditors to tell so, not us, because there are these companies that we work with, certain certification bodies. Those are the ones who tell us Class 2, 8.5 meters, kilometers per hour. So that can last 25 years. What happens after 25 years? 25 years plus X depends on the loads that the turbine will go under. It depends on the loads. There will be plus or minus years, of course. I mean, it's not like we will come and tell you to disassemble and dump it in 20 years. We have E40s, for example, established, erected them in 1998. They're about to accomplish their 20th anniversary, and no main components so far has been changed. Same components, same generator, same everything. And about the previous question, for example, generators, 25 years of design capacity. If that's 4 megawatts after year 20, will it go down as to 3.8 in terms of generation? No, it's not the case. It's not going to happen. But there might be minor damages or whatever on the blades. There might be certain changes. But as I said, these are minor things, very, very minor. But generally speaking, we don't have a condition, and it's not an extra cost on investors. And in Ercon, we want to think our investors in the long term. Wind energy, long term business. When you consider that as a long term business, you can achieve the targets, the goals that you're aspiring. Thanks. Well, Vestas started work in 1979 on gearboxes, the gearbox systems. Since 1979, we are developing these systems and products. But regarding alternative options, yes, we are open to alternative generation or manufacturing options. I would like to say two things. Two different types of designs. I mean, that's the rule of the game. But it does not necessarily mean that one of them is good and the other is bad. No. No, I mean, I think you would agree with me, dear colleagues. Both design preferences have their upsides as well as their downsides in themselves. Not in comparison with one another, but Vestas prefers gearbox power transmission systems with correct engineering. It provides you with an independent and a less costly option. Gearbox systems in 1990s have gone through a lot, quite a lot. There has been a great amount of learning, and since then, the turbines which have been developed, I mean, the gearbox systems, not only Vestas, all the suppliers and everyone, but gearbox systems, until those systems, we have gone through all the problems that were there waiting for us. Now there's a new learning curve, but we have learned a lot of valuable, valuable lessons. And about question one also, design life and field operation life and afterlife, so to speak, after operations. I think John said this. It depends on the wind conditions, on the topography and climatic conditions on site. So you have to reflect all of these things in the feasibility and with the company discuss these issues. In the market, you have type certification companies issuing competence certificates for 25, 30, 35 years. You have such designs, yeah. You have them. But this doesn't mean that it's designed for 30 years of service. That necessarily will not perform as good as always. Of course, small modifications can always increase the life of such devices. But if you have climatic conditions that are less and less harsher than the design criteria, then the operation life can be even longer, 30 years, 40 years, whatever. So it is exactly when you should go and talk to your manufacturer, discuss this issue with him. In terms of certification life cycles, that's one thing. That's one thing and separately, but after that you have metal fatigue, whatever, and all those that need to be taken into consideration. That's something else. There are certain sites where 20-year guarantee will just vanish in 10 years, but you have certain margins. You can use class 1 products in class 2. For example, you can move all ours to Cheshire, and they will still operate there for 10, 12 years. So it all boils down to the turbine company, but extreme loads is the concern. Fatigue loads, and you can sort these out I mean, fatigue can be sorted out with certain calculations, but extra loads, extreme loads, will it bring down the turbine? Then you can carry out calculations, fatigue calculations, but you have to go and talk with the manufacturer on site. Any other questions? Well, let's have a final question, the last one. And my friends are warning me that we're out of time. I'm sorry, the microphone is off. About the gearbox system. Gearbox system and direct drive system. What is the total energy loss? Is there a comparison? Think about the gearbox and the direct drive system and energy losses. Is it any different for the entire life cycle? Here's how it is. Both technologies, we know their nominal powers, we know the outputs, that's the output guaranteed. Any energy loss, I don't think we've encountered anything like that. No, I mean that's not going to be a wise comparison, by the way. But I haven't seen and heard of this before. I think your groundwork should be, if you're talking about 3 megawatts of direct drives, for example, direct drive technology for 3 megawatts, and it will run for 20 years, and its degradation or capacity degradation. Is that the case? And no, it's not the case for direct drive. It's not the case for the gearbox system. But as Mustafa clarified, depends on the field, on the structure of the wind. So each turbine has to be taken into consideration individually after regular maintenance. Both technologies and the energy losses in both technologies and degradations, of course, have to be measured and supervised. Distinguished participants, thank you. Thank you for your patience. Thank you for bearing with us. And the panelists, thank you for informing us. And inshallah, in the near future, in the upcoming days, we will have, I mean, those days will favor us, the investors, the designers, and everyone. Thank you.